But our next talk, our last talk for today, is Kayun Ho, at Northwestern University, who is going to present work he's doing on a log structure Duval connector.
Hi. So it's a part of an ECP project. We are doing a log-based BLL. The reason we start this project is we observed some performance bottleneck on the parallel I/O in HDF5. So basically what we do MPI collective I/O is the data is being reordered into the canonical order that matches the HDF5's dataset layout and the file format. So if we have some non-contiguous I/O pattern like slicing a very high dimensional data set, then we'll generate a lot of non-contiguous I/O pattern on the HDF5 file. So consequently, the MPI collective I/O internally need to perform a large amount of communication to reorder such I/O pattern to match, in turn match the striping of the parallel file system. Currently, HDF5 to provide a chunk of data layout that somewhat reduce this issue, but it requires the use of B-tree for indexing, and we still observe less than ideal performance on part of the application that actually generate a huge amount of such non-contiguous I/O pattern. Also there's lack of API for like accessing multiple data set at once, or allow different process to access different data sets in a collective H5 read or write code. So during our previous project, we studied log-based storage layout. So basically, the storing the dataset in log structure means just appending the data one after another as is given by the application. And instead of reordering the data to match the file layout, we record additional metadata to describe where the data should go logically fit the HDF5 format or the semantic. So by doing this, we effectively delay the reordering overhead to when the data need to be read, instead of having to reorder it to write to the file. The major advantage of log style layout is the write pattern is always contiguous in file, regardless of what the application do, and regardless of what the library do. We always write contiguous space per one block per process, and contiguous space combined. So we've seen log-based storage layout employed by many other libraries like RDOs, and PNetCDF also has support of it, and logfs is a MPI ADL plugin that basically redirect MPI traffic into a log-based storage layout, and there is a PLFS implementation also for the file system level. For the applications, we also see many AMR-based applications that use this pattern that actually generate result in very efficient I/O performance. We saw this on AMRX and the Flash code. So with this experience, we are thinking about whether we can apply the same idea to HDF5 and benefit from a lighter and more efficient storage layout. So we come up with this the design of log-based VLL. It's basic. It's literally a pass-through VLL that direct everything to the native VLL except for the data set. So the architecture looks like this. Every single log VLL gets it, translated it into the into native VLL code. But unlike the actual pass-through VLL that pass everything as is, we translate those APIs so the data set is always stored in a contiguous layout. So what happened when the on the data set operation is for everything other than data set, we the log-based VLL is exactly the same as the pass-through VLL, except for the data set. If there's a D-write operation, we don't actually write to the data set, but we append the data to a log, which is basically implemented with another one-dimensional data set that serves as a free space for the data. And also we have a different log for metadata alongside the data log to record this operation. We use the native VLL so to handle HDF5 file. It ensures the file format is consistent to the HDF5 specification. So in case there's a change of format or a new feature added to HDF5 will be compatible to that. But for data I/O, we use MPL directive for performance issue. So basically, when we have a data set created for either the log, that is the data part, or the metadata log, that's the metadata part of the write, we retrieve its data set offset in the file from the native VLL and write the data with MPL directly to reduce the overhead of HDF5 state. So our VLL file format is basically a format that built on top of the original HDF5 file format. So the file written by our VLL are all legit HDF5 file and can be opened by any application, but the content is only understood by our VLL. So this design ensures we have a consistent behavior for non-dataset operation like group, link, and attributes. So that keeps the compatibility high for existing applications. The way we handle, because we redirect all the datasets write data to the log dataset and the metadata dataset already. So we don't actually need the space in the dataset itself. So to save space, we make every dataset scalar and we record its size as attributes. The log dataset and the metadata dataset is placed in a hidden group right under the root group. And also, we also place other metadata required for use internally by the VLL in the log group. The data set right in the log-based view is always aggregated. That is, we change the semantic of H5 write and read. A call to H5 write and read does not actually perform the I/O, or nor does it perform communication, but it only record the write request locally. Means stage the write request and the I/O request with the VLL. And the staged requests are flushed when the file is closed, or when user specifically call H5F flush or D flush. So doing this means every D-write and D-read are independently handled by each process. That means the application can have different process doing I/O on different data sets, and it can also have access multiple data sets before actually calling flush to flush I/O. We observe a significant performance improvement on some applications by being able to access multiple data sets at once. Regarding the staging and the flushing, we introduced two new property lists. The first one is for aggregation. That is to catch the user that are temporary in the VLL. We need to copy to an internal buffer. But we will observe that for many applications, they actually do not reuse their I/O buffer throughout their I/O session. So we offer the first property to allow the application to use their own buffer. That means the buffer will not be modified until they close the HDF5 file. This avoids the need to copy the data internally and improve the performance for those applications. The second is regarding a limit on amount of memory the VLL can use to stage the I/O request if the user buffer is if the application intends to change the buffer after staging. So to read the data set, if there's a read request, the VLL will search for the metadata data set entry by entry, and for each entry that matches the corresponding data set identification number. We find the intersection and generates MPI subarray type to read the corresponding data in the log data set. We have some, we're considering some method on speeding up this metadata search. One is by sorting the entries according to dataset ID or process who write it. Another is have a B tree like a tree-based index for this metadata. The difference to chunk the data sets, the B tree is actually in the file, but for this tree-based index, we are constructing locally in the memory. Also, there is a utility to convert log-based VLL file into a traditional HDF5 file, so it can be read by all applications. This design currently, there are some limitations in our implementation design. The first is, since this is for parallel I/O performance, we require it only work with MPI I/O. So at this time, if the user want to use the log-based VLL, they need to set the file access property with MPI information. And we assume all metadata operation is collective. That means every group data set, attribute, and link, create, open, and close, they are all assumed to be collective. But data operation, such as data set and attribute, right, they can be independent. And the final and the most significant limitation of log-based DLL, and I think apply to all log-based storage layout, is the file, it inflates the file size because additional metadata we need to keep. So in our current implementation, one metadata entry, that means one DRI request per process per selected block, selected hyperslave, that will require for around 40 bytes of metadata. So in a very extreme case, like the application is accessing a data set cell by cell, we will see the metadata significantly larger than the data, and the file size can increase by many times. Finally, there's a case study. The first one is the application that motivated this project is the HDF5 climate simulation model. We developed a benchmark based on its I/O pattern for PNetCDF and NetCDF4 and the HDF5 directly. So basically, the application is facing a large amount of non-contiguous file writes, and each write request are small and fragment. So it will be inefficient if every data set in HDF5 data set is declared contiguous. Also, it has a larger amount, like hundreds of data sets to write. The data is spread across hundreds of data sets. And to make things worse is that the number of data set write requests per process is different. So that with current HDF5 implementation, that means either they must use they have to use independent data set writes for at least for the difference part of the I/O request, and that they can only write one data set at a time. So we will observe very slow performance on this and on our larger test data, it cannot finish in a reasonable time with the native HDF5 implementation. We will run this with the atmospheric component, which they call FCase in the E3SM application, with any 120 resolution. That's the highest resolution and the largest data we have so far. We tested on Cori with 32 Haswell node and the total of 1024 process. The latest stable release of HDF5, and we have all processes performing I/O, because in E3SM it's configurable to have some processes perform I/O and some do not. So in this configuration, we have all performed I/O. It's a preliminary result, so it's based on our current prototype, and we are still working on optimization and improvement. So we can expect this result to be improved in the final version. You can see that for 14 gig of data across all the data set, it takes 31 seconds to write, and a significant portion of that is in posting the I/O request. also the VLL allows posting the requests before flushing them. We found the posting overhead is still somehow high, and we are currently working on reducing the overhead for posting. And the next one that's significant is the metadata. Because of the I/O pattern, we actually found the size of metadata non-negligible in this case. So the second chart shows the file size, and that is the file size for the assumed file size if it's in the contiguous storage layout. The second column shows the file size generated by log-based VLL. We can see a 8.4 gigabytes of difference that is overhead on the metadata, and about half gigabyte per second effective write bandwidth when we adjust it for the inflation of file size. And finally, the final benchmark is a simple one. This one is we use the IOR benchmark with a simple setting 1 megabyte block and transfer size, 32 block, and a smaller scale run with only 8 nodes, also the latest HDF5 implementation. So with this simple pattern, now the HDF5 native VLL can finish in a reasonable time. So we have a side-to-side comparison of 8 gig of data written by log-based VLL and the native VLL. The metadata in this case is negligible, so it's not showing here. Okay. Finally, to end this presentation, we give an example code for using the VLL. So basically, the VLL can be used by programmatically setting up the FAPL, or alternatively, it can be built into shared library and enabled by environment variable. Okay, I think that's what I have. Thank you.
That's great. Thank you, Kayan.